1.2 Uncertainties and Errors. We'll be starting with random versus systematic errors. But first, it's important to distinguish between precision and accuracy. So values are considered precise when the range between recorded values is minimal. Values are considered accurate when the recorded values are close to the actual value. You can be precise while being inaccurate and accurate but not precise. Precise while being inaccurate means that there is a presence of systematic errors, and accurate but not precise means that there is a presence of random errors. Here are some graphs to illustrate the difference between precision and accuracy. With that in mind, we distinguish between systematic and random errors. So as said before, systematic errors may be precise but inaccurate. Systematic errors are errors that result in a bias in the same direction. In simpler terms, the measurement will be consistently more or less than the expected value. An example of a systematic error is the zero error. This occurs when the measuring device is measuring more or less than zero before measuring, resulting in values consistently being greater or less than the actual value. Random errors usually affect precision and less of accuracy. Random uncertainties, unlike systematic ones, can be biased in all directions. They may be a result from things like human error, poorly designed experiments, or literally a random thing happening which cannot be explained. Random errors can be minimized but not completely removed from an experiment. Moving on to uncertainty when dealing with data manipulation. First, we begin by calculating the uncertainty in an average. In order to calculate the uncertainty when calculating averages, we take the range of the values and divide it by 2. For example, if we are given a set of values, which are 10, 9, 10, and 11 here, the range is 2 because the range is 11 minus 9. So the uncertainty is 11 minus 9 all over 2, which gives us an uncertainty of plus minus 1. Uncertainties exist in 3 forms. We have absolute uncertainty, fractional uncertainty, and percentage uncertainty. When given a set of data, the absolute uncertainty is the uncertainty of the measurement. For example, the uncertainty in the ruler, the uncertainty of the weighing scale, and more. In an average, the absolute uncertainty is the range over 2. The fractional uncertainty is the ratio between the absolute uncertainty and the measured value. And the percentage uncertainty is the fractional uncertainty multiplied by 100 to get a percent value. So here's an example. We're told to calculate the absolute, fractional, and percentage uncertainty for the following measurements of a force. So to solve this, we find the average value, which is 2.63 newtons. This is rounded to 2.6 newtons. The range in this case is 2.8 minus 2.5, which gives us 0.3 newtons, giving an absolute uncertainty of 0.15 newtons that rounds up to 0.2 newtons. We would write our value for the force as 2.6 plus minus 0.2 newtons. The fractional uncertainty is 0.2 over 2.6, which gives us 0.077, and the percentage uncertainty will be 0.077 times 100%, which is 7.7%. So moving on, we have adding and subtracting. In adding and subtracting, we just add the absolute uncertainty of each one. For example, you measure the weight of 2 filter papers before and after an experiment. The mass of the sediment remains in the filter paper after the experiment. This is the values that you get. And you're told to calculate the total mass of the sediment in the filter papers. We'll give you some time to try and solve this. So by now you probably have figured out that in order to solve this, we first add the 2 masses of the filter papers and then use this to subtract the 2 masses of the filter papers before, which gives us 0.1377. And for our uncertainty, it's simply the sum of all of the other uncertainties. So in this case, we would have an answer of 0.1377 plus minus 0.0004 grams. The same can be said for multiplying and dividing. However, in multiplying and dividing, the fractional uncertainty of the final value is the sum of the fractional uncertainty of the other values, which can be illustrated in this example. So the sides of a rectangle are measured to be these values, and you're told to find the area of the rectangle. In this case, the fractional uncertainty in A is roughly 4%. The fractional uncertainty in B is 2%. Thus, the fractional uncertainty in the area is the sum of these two percentages, which gives us 6%. Moving on, for an exponential equation, the fractional uncertainty of the final value is the fractional uncertainty of the first value multiplied by the absolute value of the integer. For an equation with a root, it is the fractional uncertainty of the first value multiplied by the inverse of the root's power. What does all of this mean? We'll illustrate it in this example. First, let's adjust the equation a little. We can write it like this. Now, using the division and power relationships, we notice that it gives us this relationship instead. So the percentage uncertainty in T will be half that in M plus half that in K. This means that the percentage error in T is 0.5 times 5% plus 0.5 times 11%, which gives us 8%. If the measured value of T is 1.2 seconds, then the absolute uncertainty is 1.2 times 8%, which gives us 0.096. This rounds up to 0.1, and so we quote T as being 1.2 plus or minus 0.1 seconds. Remember that the quantity and the uncertainty must be to the same number of decimal places, and so the zeros are important, as they give us the precision in the value. Now we move on to the uncertainties in graphing. When graphing uncertainties, error bars will be formed. These are lines that are parallel to the x and y axis to represent the uncertainty in each value. When drawing best fit lines, they need to fit inside the shaded area shown in the second diagram. Best fit lines usually are drawn by eye, but certain applications can do it for you too, like Logopro, Google Sheets, or Microsoft Excel. Since you're taking IB Physics, I'm pretty sure you already know how to calculate a gradient, which is the difference of the y-axis over the difference of the x-axis. In order to calculate the uncertainty of the gradient, we find the difference between the maximum gradient and the minimum gradient and divide it by 2. The maximum gradient is from the bottom of the first error bar to the top of the last error bar. The minimum gradient is from the top of the first error bar to the bottom of the last. In this example, the blue line has a gradient of 210 newtons per meter and intercept at negative 0.18 newtons. The red line has a gradient of 193 newton per meter, and the intercept is a positive 0.13 newtons. So we can find the uncertainty in the gradient as 8 newtons per meters. Talking about measurements and uncertainties, it's also important to consider the micrometer screw gauge. The micrometer screw gauge is an instrument used to measure really tiny things like the width of a wire. You place the object inside it, secure it, and twist the thimble until it is secure. In this example, you read the sleeve and find that it is 6 mm wide. Then you add the value of the thimble, which gives us another 0.68 mm. This totals to 6.68 mm. In the next example, we see that the sleeve gives us 7 mm and the thimble gives us 0.47. This totals to 7.47 mm. Thanks for watching. Goodbye, don't die.